Hello everyone, my name is Yongjin Soo from Gyeongbuk National University in Korea. I'm so glad and excited to give a talk about our work at Sigmatric 2022 this year. In this work, we've conducted rigorous empirical studies across multiple GPU-DBMSes regarding their query performance. So my collaborators are Junyoung, Byung-chul, and Gapju. Let's get started. Here are the contents I'm going to deliver in this talk: introduction, model, evaluation, statistical analysis, implication, and conclusion and future work. As you know, GPU has gained much popularity from a lot of different communities, including data management community, thanks to its massive parallelism and high bandwidth. I'm showing you the picture about the GPU cards we configure in our server, and we notice its amazing performance as well. Accordingly, the database community has been making strenuous effort to accelerate the analytical query processing capability by jointly harnessing the power of a CPU and GPU. At last, several market players appeared and realized their GPU-based systems such as Blazing SQL, Omniscience, Kinetica, SQReam, and PGStorm, and so forth. Also, many academic prototype engines appeared, Hive, GPL, HTAP, and so forth. In this regard, several research questions arise in terms of its query performance. For instance, what factors affect the query evaluation, and how do they interact? Does a newer GPU model provide better performance compared to its older generations? Does GPU DBMSes support a wide range of queries for more variety of analytical tasks? What about multi-GPUs? What about scalability over increasing data? Is low utilization of GPU problematic in these DBMSes? While trying to answer these questions, we found that there have been few studies to be able to answer these questions. Therefore, to fill this gap, we have conducted this empirical study. So after reviewing a rich body of existing papers, we have found a number of factors, and we just identify some major key factors affecting query performance, and then we build and propose this causal model to include them and show their associations and explain the variance of the query time. So this model is designed to explain and indicate how query time on a GPU DBMS may vary. This model includes 4 major constructs such as hardware, query, data, kernel complexity, and kernel complexity construct. And each construct has its specific relevant variables. We have a total of 13 variables, and 8 of them are independent variables, and 5 of them are dependent variables. And note that for some variables, they correlate with each other. For instance, number of GPU cards negatively correlates with kernel execution time. On the other hand, scale of the data volume positively correlates with 4 variables, including this construct, and so on. In this model, we present 5 major hypotheses with 17 specific correlations. And note that this correlation has its direction. So the left-hand side indicates is the source, and the right-hand side indicates the effect by its reason. So we've got 12 positive correlation and 5 negative correlation. Now the question is, how can we validate this model? So to do so, we have operationalized the variables by setting values of these variables or measuring their values. And then we have run extensive experiments as to be described shortly. for this, for our experiment, we studied 3 different GPU DBMSes, such as Blazing SQL, Omniscience DB, and Pidgeotron. We used their stock configurations. Of course, there were several other candidates we could consider. However, they were not included in our study because of that. Because they were deprecated. They were not compatible with our configurations, and some code was not open sourced, and it was commercial. We applied our timing methodology for getting high quality, measured data from these GPU DBMSes, and this procedure was inspired by my prior timing work published in this DBMS. So along with this timing procedure, we have a series of interesting experiments across these DBMSes to better understand their behaviors. Our first experiment concerns the impact of advancing GPU or evolving GPU models in terms of their query performance. For this experiment, we ran on a complete set of TPSH queries, as shown here, and over a series of different GPU models that evolve. As a result, overall, there was tendency to improve the query performance as GPU generation evolves, as can be seen Q1, Q9, Q14, Q19. However, there were some queries that couldn't be executed at all in older generations, like 10,080 and 20,000. The 20,080 Ti and so forth. Even though we used most up-to-date device 3090 was used, there were some queries like Q13 that ran rather slower compared to the earlier models. There seems much room. There still is much room for improving their performance based on this experiment. We also extended this experiment by considering another benchmark, such as join other benchmark. And then interestingly, Omniscience could not run any job query because the Omniscience DB couldn't support an aggregate operator on text type of data. And also, for some queries, these DBMSes couldn't execute. These queries couldn't be executed by any of these DBMS because of various reasons, such as parsing error from brackets, including a query, and also supported the aggregation as I described in Omniscience DB, and being unable to handle large text data. So these results indicate that we still more engineering efforts to support a more variety of analytical tasks. And also we ran the multi-GPU experiment using TPSH across different DBMSes. Unfortunately, we couldn't get any data from Blazing SQL and Pidgeotron because of their errors, and specific in particular Pidgeotron required a commercial license, so it was not possible for us to purchase it, and then we couldn't run the multi-GPU experiment on Pidgeotron. It was the only Omniscience DB was the only DBMS that could run normally with multi-GPUs. So overall, its improvement was a little bit. However, its significance was not as big as we expected. And also, the dual mode wasn't successful in running in Q21 and Q22 because of the same reasons as I described it previously. So more engineering efforts seem needed for exploring multi-GPUs in these DBMSes. The next experiment concerns how scalable the GPU DBMS is over growing DBMSes. From our experiment, we could see several serious concerns specifically observed in Omniscience, SQL, and OmniSign DB and blazing sequel. So as you can see here, beyond SF128, 64, we couldn't run any query on blazing sequel, sorry, the Q1 couldn't be executed on the blazing sequel, and also it couldn't be the Q2 also wasn't executed as well. And also OmniSign DB overall showed best performance on the most up-to-date device. However, it showed serious scalability concerns in between 16 and 32. In PGStrom, we could see overall better. We could see the performance was better than the others. However, when it comes to its scalability, PGStrom was not bad. However, its overall performance was not better than the others. So we need to improve it. And also, the last question on the last experiment concerns GPU utilization. So we wanted to examine how where their query time was spent during entire query execution. So as a result, overall, 35% of the query time was spent on GPU. And the blazing sequel was the DBMS that most utilized GPU. It was about 87%. And also OmniSign DB and PGStrom still suffered from GPU underutilization. From this experiment, we could see several implications, such as we've got to improve better utilization of GPU during query execution, and also we should be able to offload more parts of query evaluation pipeline on GPU so that we could exploit maximize parallelism through GPU. Let me now talk about our statistical analysis results. From our experiments, we could obtain real empirical data, and then we perform a strong statistical analysis using our methods. So as a result, as shown in this table, all hypotheses included in the model are statistically significant. Among 17 cells, we got 6 green cells and 11 yellow cells. The green indicates its correlation strength is higher than 0.3, and yellow indicates that this correlation strength is a little bit lower than 0.3. Although there were some differences in these correlation strengths, our results provide strong empirical support for the validity of our model. One thing I want to mention is that not only the data transfer time, but also kernel execution time are essential factors affecting query performance. So we should be working, more on to further reduce kernel execution time to improve the query performance in these DBMSes. We also perform regression analysis. As a result, we got 77% of amount of variance explained on the query time. This indicates that all other potential reasons affecting query time in the GPU DBMS will have less explanatory power than the variables we took into account in our model. And also we extended our regression analysis on these variables. As a result, we could see their the contributions to varying the query time. So we need to be also paying attention to further improving these measures as well. From our study, we could obtain several engineering and research implications. First one is its importance of reducing the kernel execution time. Our model indicates the kernel execution time, as I described, is an essential factor as a data transfer time in reducing the query time in the GPU DBMS. In addition, we need to we should not overlook the effects of other GPU-specific variables, such as number of GPU cores, amount of GPU memory, number of page faults, and so forth. So these factors are also should be treated very carefully. Next implication concerns performance dependency of the type of GPU device. Overall, the more advanced model delivers the faster carry time. However, using the most up-to-date device doesn't necessarily guarantee its optimal performance. So not only hardware support, but also software support and user support are necessary to exploit the performance of these DBMSes for our query acceleration. And also there is a clear sign of limited scalability, mainly attributed to limited GPU memory. One of the biggest the bottleneck related to this is the lack of device memory. So we've got a device better and the more efficient way of handling the data loaded and generated in the GPU memory during our query evaluation. And also there are several remaining issues such as low utilization and support of a variety of more variety of query operators that we need to overcome. Now let me conclude my talk. In this paper, we have conducted a comprehensive empirical study across multiple modern GPU-based systems, DBMS systems, for better understanding their behavior. So to make our work more realistic, we use TPCH and join all the benchmark queries. In this work, we have explored several factors, and we explored many factors and identified some major key factors affecting the query time. And we proposed the structure causal model to explain the variance of the query time. As a result, our empirical data provide strong support for the validity of our model, and we were able to identify several performance concerns as discussed here while running our experiments. So we need to improve these issues. In future, we could take into account several factors such as several factors, cache size indexes, and server grade GPU and other profiling measures. And also our work can be extended to any other GPU-based system. Thank you for listening. Let me now take your question.